Okay. So let's get back. So you remember, where were you? So given a neural network, the output of the neural network is computed getting the output of the neural network, but we are talking about now the output of just one neuron, okay? Neuron J. Remember that the output layer can have more than one output neuron. So consider one neuron, the output is computed getting the linear combination of inputs and weights and using as argument to a nonlinear activation function, okay? Okay, but when we compute this output, how do we correct the weights? Well, we'll use the backpropagation algorithm. And to calculate the correction, the amount of correction we are going to apply in a weight, okay, we use this derivative, okay? So opening this derivative here, okay, we see that each partial derivative depends on an output of the network, a part of the network. So we see that the general error depends on the error of the neuron. The error on the neuron depends on the output of the neuron. The output of the neuron depends on the activation potential, the linear combination, and the linear combination depends on the weights. So we can verify each of the derivatives here, each of the partial derivatives, okay? So here what we are doing, we are differentiating the equation on both sides, okay? So differentiating the error here, okay, in the direction of the error on the neuron, we get only the error on the neuron. Okay, I'm not going through in the mathematics into much details, okay? I'm just showing to you how the derivatives, the partial derivatives work, okay? We know that error is a summation over all the errors of the neurons. So applying the derivative on both sides, we get just the error of one neuron. Nice. Now let's go. If we get the error, we know that the error is the desired output minus the predicted output. Okay, if we make the derivative on both sides, we get that the value is -1, because if we, okay, derivate this error in the direction of y, okay, this is a constant, okay, this y here disappears, we get just -1. Good. So we are constructing our updating formula, updating mathematical formula. Now, you see the output of the neuron is calculated getting the activation potential using as argument to a non-linear function, okay? Okay, differentiating the equation on both sides, what we have here is the derivative of the activation function with relation to its argument. Okay, so up to now, what we have? We have the error, we have a -1 sign, and we have the derivative of the activation function. Okay, let's continue. Yeah, and now the activation function is just a summation, okay, of weights times inputs. Okay. Inputs of the neuron, right? So differentiating both sides, we get that if we differentiate this with relation to W, okay, we will, here differentiating the relation with W, what's going to remain? Only the Y, right? This disappears, only the Y. So we have the error, a minus signal, the derivative of the activation function, and the signal that's going in the input of the neuron. Now let's put all these things together. So the derivative of the error in the direction of a wage is minus the error of the wage multiplied by the derivative of the activation function multiplied by the signal that's going in the neuron associated, okay, with this wage WY. So WJY is a wage connecting two neurons, okay, J and Y. Is it okay up to now? So we are getting closer to that formulation. Remember, a learning rate times an error times what's the signal that is used as input in the neuron. We're getting closer to that formulation. Okay, let's continue. So the correction that's applied to a wage is defined by what we call a delta rule, okay? So the correction we applied in a wage is minus a learning rate multiplied by the derivative of the error that we want to minimize in the direction of the wage. So do you remember this formulation? We already saw this, okay? So this is the learning rate, and the negative signs here stands for the gradient descent, okay? Okay, we know that the derivative of the error in the direction of the wage is this formula here. So what we are going to do, we are going to put this here. So we have a minus here and a minus here, so it disappears, a positive sign. And now what we have a learning rate times here what we call a local gradient of the neuron J multiplied by the sign that's going into that neuron, okay? So the local gradient associated to a neuron is the error times the derivative of the activation function in that neuron. Is it okay by now? So we have a neuron, an artificial neuron, okay? We know the activation function of that neuron, okay? That's associated to the output of that neuron. We know it. We know that it's a nonlinear and differentiable function, and we know the derivative. Knowing the derivative, we can make the calculations. Okay, we don't need to find the derivative. The derivative is known. We just put in the code. Okay, the error we know how to calculate. Desired output minus the predicted output, and this signal that's entering in the neuron we also know. So we just have to make the calculations. Okay, good. So as I said, so the local gradient of a neuron is defined by the error in that neuron times the derivative of the derivative of the activation function, okay? With respect to the argument. So this local gradient here, that will define the necessary change in the weights, okay? So the change in the weights depends on the gradients, the local gradients associated to each neuron, okay? The product of the error and the derivative of the activation function. Good. So the error function now, we know that it's a key factor to calculate this wage, okay? So we have two cases to calculate the error into a neuron. When the neuron is located in the last layer, when the neuron is an output neuron, it is located in an output layer, then it is easy to calculate the error associated to that neuron. Okay, because we have the desired output for that neuron. But if the neuron is located in a hidden layer, we don't have the desired output for that neuron. So to adjust the error in a hidden neuron, we depend on calculating the local gradient of its next neuron, the neuron that is ahead of him, okay? So I calculate the beginning in the output layer. I'm going to change here just a little bit. There are some drawings in the slides, but I like to draw here. Should I turn on the lights? Okay. So, I'm going to draw here a neural network. Nice. Okay. So all the neurons here are associated to all the neurons in the output layer. So this is the output, okay, and this is a hidden layer. Nice. So what happens? For a given output neuron, I know the output and I know the desired output. So the error is easily calculated, okay? Desired output minus the output of the predicted neuron. Okay, given this, okay, we know that we know the activation function. So we know we can calculate the error, and we can calculate, okay, times the derivative. I don't know how to draw this. I know, I'll put just a D here, okay? The derivative here, I will use this symbol, of the activation function, okay? We know how to calculate this, and this is the, let's call here, the gradient, local gradient, okay? So we can do this for all the output neurons, okay? So this is the local gradient 1, this is the local gradient 2, and this is the local gradient 3. We know how to do that, okay? For the output. But what about now? We don't know how to calculate the error here. The only thing we know here is the derivative of the activation function that we know how to calculate, okay? The derivative of the activation function, because we have a V here, of course. Yeah, we have the output of this neuron. So what we are going to do is that we are going to calculate all the gradients, local gradients here, and we know that we have here a W, another W, and another W, okay? That connects this neuron with this tree, okay? So we are going to do gradient times W, gradient 1 times W1, gradient plus gradient 2 with W2, plus gradient 3 with W3, multiplied by the derivative of the activation function in this neuron. Okay, and for our lucky, we know the derivatives. We don't have to calculate them. Okay, and the packages do this for us automatically. We're not going to implement it by hand. I mean, if you were computer scientists, I would do that with you, but not today. I never, oh yeah. Okay, so we have two cases, okay? Hidden neuron and output neuron. So I'm going to show you here what I just draw, okay? So for a neuron in the output layer, then it's easy. You just get the error associated to the neuron. Easy, easy. Then you just compute error, multiply it by derivative of the activation function. Okay, so you do this for all output neurons. Okay. But what if neuron J is a hidden neuron? Okay, so there is no specific desired output associated with this neuron. So what you have to do, okay? You have to recursively calculate the signal that goes back in the neural network in terms of the error signals of all the neurons that are connected to it. See? Now, the development of the backpropagation algorithm becomes a little bit more complicated, but it's not that complicated, it's easy, okay? So, let's see here. Here you have an output neuron, and here you have a hidden neuron. So for the output neuron, you just calculate the error. Okay? Nice. Calculating this error, you can calculate the local gradient associated to this neuron. Okay? So for neuron J is connected to all the neurons here, all the output neurons. So I'm just going to perform this kind of calculation here. I'm going to calculate the local gradient for the output. And then as each neuron is connected to the previous neuron here by a weight, I'm just going to make a multiplication, okay, of the local gradients times the weights that connect these output neurons to neuron, in this case here, J. Okay, and then multiply that summation by the derivative of the activation function in neuron J. So you see that what I have here is an estimative of the error that I have here. If I have another previous layer here, I would have an estimative of the error. Okay, so this is why there are some problems related to using very deep neural networks, like these local gradients, they start vanishing as you go deep and deep in the network. So that's why we use another activation functions and another techniques to try to avoid this kind of problems, okay? In deep learning algorithms, I'm pretty sure that you've already heard about deep learning. We use other activation functions that we are not going to use here. Actually, we are going to use one, I believe. And then other techniques, okay? Anyway, so this drawing here shows exactly what I draw here, okay, this picture. It's a graphical representation. So, see, the local gradient of this hidden neuron, okay, is just the summation here of the local gradient of each of the output neurons, okay, weighted by their respective weights, multiplied by the derivative of the activation function in this hidden neuron. Is it very clear? Nice. So summarizing, so the correction that we are going to apply in the weights connecting two neurons, okay, has this formulation. It's a learning rate times a local gradient of the neuron times the input signal that's going to that neuron associated to the weight. Okay. For output layers, we can easily calculate the local gradient. It is just the product of the derivative of the activation function and the error signal. Okay? For hidden layers, then we calculate the derivative of the derivative of the activation function associated to the neuron, and we just multiply by all the local gradients that were calculated in the layer ahead. Okay, nice. So let's talk about activation functions now, okay? So to calculate here the local gradients for each neuron, we need to know the derivative of the activation functions that are associated to the neuron. Remember, for the derivative to exist, okay, the activation function must be continuous, okay? So it has to be it has to be possible to calculate the derivative, okay? So differentiability is a requirement. Good? Now, So a common function that is used is the sigmoidal. Okay, usually we use two sigmoidal functions, logistic and hyperbolic tangent. Nice. So this is the logistic function. Okay, so this guy here is the activation potential. Okay, that's just the linear combination of wages and inputs. So we just give two exponential here, 1 divided by 1 plus the exponential of minus the linear combination. Usually this a here, this constant is 1. Okay, and what happens to this activation function? It shrinks, okay, the output of the neuron to be between 0 and 1. Okay, so for example, this is good for classification. Suppose I have 10 classes in my problem. I can work with 10 neurons in my output layer. Okay, then the classification will be the higher output. All the neurons will be as output values between 0 and 1. I just get the higher output. That gives me the classification because I associated each neuron to one class. Is it clear? Okay. And we know the derivative of this function. The derivative of the function, okay, with respect to the argument, that's the linear combination, is given by just the output 1 multiplied by 1 minus the output. We know this derivative. It's easy. Questions here? Is it okay? Nice.
What's A again?
A is a constant, usually 1. Okay, because A we have the logistic function here, right? Is it okay? So 0, 1, né? Shrinks. That constant gives us the smoothness of the, you know what I'm talking about. The smoothness of the function, okay? But usually we use the value 1. Okay, it changes the curvature, okay? Nice. Well, so given the logistic function, the derivative of the logistic function, okay, for a neuron that's in the output layer, so the output of the neuron is the output of the neural network, okay? So the local gradient, remember the local gradient is the error multiplied by the derivative of the activation function. We know the derivative of the activation function, okay? The derivative of activation function is the output, 1 minus output. It is here. And here I'm just putting the error, right? Error here. And the A that was here was just thrown in the beginning, because a constant, okay? Nice. Good. If the neuron, okay, is in the hidden layer, then the local gradient of the neuron is given by this formulation that we saw already. This is the output layer, the local gradients for the output layers, and this is the derivative of the activation function in the hidden layer. Okay, so we know the derivative here. Here is the derivative. We just multiply the derivative by the local gradients in the hidden layer. Okay, nice. Another activation function that we can use is the hyperbolic tangent. Okay, again, A and B are constants. Usually we use 1, the value 1. So it's just the hyperbolic tangent of the linear combination of wages and inputs, okay? And the hyperbolic tangent function limits the output of the neuron to the values -1 and 1. So for example, this is good for a classification problem as well. For example, suppose you are working with a classification problem and it has 3 classes. You can have just one output layer, for example. And then if the output of the, you can have one output layer with one neuron, only one neuron. If the output of this unique neuron is -1, then it's one class. If it's 0, it's another class. If it's 1, it's another class. Okay? That depends on the problem you are using. So we also know the derivative. So the derivative with respect to the argument is given by this. Okay. Again, these are constants. Okay, so what we usually have is 1 minus output, 1 plus output. 1 minus output multiplied by 1 plus output. Usually, this is the derivative of the hyperbolic tangent. Okay, and again, we have different formulations, like, for example, if the neuron is located in the output layer, then the local gradient of the neuron is given by this formulation here, okay? The error we know how to calculate, and the derivative we know how to calculate, okay? O here means that the Y, the output of the neuron, is the output of the neural network, okay? If the neuron is located in a hidden layer, then we know how to calculate, okay, derivative of the neuron multiplied by the summation of all the local gradients of the neuron, the layer ahead. Okay, we know how to calculate the derivative here multiplied by all the local gradients in the layer ahead. Okay? So recall that I can have many hidden layers. Okay, I just compute the local gradients backwards. Nice. Learning rate. Let's talk a little about learning rate. So the lower the learning rate, the smaller the change in the synaptic waves of the network, and the smoother the trajectory in the search space. So the learning will be slower. Remember that drawing, you have the error surface, remember? And then having the error surface, you walk, okay, in that error surface, okay? So you walk faster. If your learning rate is high, you walk slowly. If your learning rate is small, okay? If your learning rate is very, very small, you can never get to a global minimum. If your learning rate is too high, you can jump the global minimum. Okay, so we have to try to find a good learning rate, okay? So the network may become unstable if you have a learning rate that's very high, okay? To increase the learning rate without losing stability, we usually use what we call a momentum constant. It's just a positive number that we multiply by the previous updating, the previous amount of updating we applied in the wages, okay? So this is a stabilization factor, okay? If the sign of the derivative starts changing for positive, negative, during many interactions, it stabilizes the learning. If the sign of the derivative remains the same, it accelerates the learning, okay? Here. So when the partial derivative has the same sign in consecutive interactions, okay, the amount of updating you are going to apply in your range grows. So I'm going to adjust the wages by a large amount. So the momentum constant accelerates the algorithms in regions where I'm going at the same surface. I'm going directly to the minimum of the error, so it accelerates the learning. Otherwise, okay, it stabilizes the effect in directions where I have oscillations in the signal of the derivative. Nice. Yeah. See, Here I have the XOR, the XOR problem. See? So with the XOR problem, we already know that with a single perceptron, we cannot, okay, here it's correct. That's the correct XOR. So we know that with a single perceptron, we cannot, okay, separate these 4 points with just one straight line, okay? But we can use, we can use a multi-layer perceptron. So we can have a layer with 2 neurons, then an output with 1 neuron. So what's going to happen is that the first 2 neurons are going to draw 2 straight lines, and this last neuron here is going to combine these lines, forming this surface. So outside I have one class, inside I have another class. Okay? And here's just a drawing with initial edges and the final edges. Do you have questions? See?
What you mentioned about if you have like a deeper network, you might have problems with the vanishing of the gradient because of the activation potential. Why is it because of this activation function?
Because
I think this part to me is
yeah, I will try to explain in more simple terms. What you have is that with time, so you have your activation function here, right? It shrinks between 0 and 1. So for example, if the output of your neuron, I don't know, is say, I don't know, 0.6. So it will be 0.6, okay? If it's, I don't know, minus 0.6, then it will be 0. Okay, it shrinks here, smoothly shrinks. But what happens is that with time, the outputs of your neuron, okay, but I'm talking about the V now, okay? The linear combination, the outputs can start to be very high or very low. And then the output of the neuron will be always 1 and 0. And at this point, there will be no learning anymore, okay? And this has the effect that with time, in big networks, you have the vanishing gradients. The gradients start to become very small, and there is no learning anymore. So what we do in other neural networks is like to use other activation functions, like, for example, ReLU. So the function ReLU is very used. There are other variations, but it's very used. And it is so the Y is going to be V, okay, if V is higher than 0. And it's going to be 0 if V is less than, less than 0, okay? So it's the max between 0 and the value V, okay? Then you may ask, but you told us that the function must be continuous. So how can I compute the derivative at this point? Because there is a big here, right? So you consider you're never going to calculate the derivative at this point, okay? And there are other formulations that, for example, smooth here, okay? So for example, if the value of V is higher than 0, then the output is V. If the value of V is below 0, then you multiply V by a small constant, okay, negative, then you have a smooth value here, you know, the activation function. So these are very used in neural networks nowadays, this kind of activation functions. Okay, they are better to work with data. good. But in simple classification problems, we can use other activation functions like sigmoid or hyperbolic tangent. Other very user activation function in the output layer is the softmax. The softmax is an activation function that models the output of the layer as if it was a probability distribution of the classes. So if you have 10 classes, okay, if you sum the output of the neurons, the summation will be 1. Okay, so you classify data in the higher output. And you consider that output as the probability of classifying the instance in that class, a given class. Is it okay? Okay, more questions? So let's try to do some implementations. Yeah, sure.
So I guess at the start I interpreted what you said about the extra layers adding these kinds of geometric delimitations and things like that as a kind of analogy, but it literally is what is happening.
Yeah.
It is drawing hyperplanes and then delimiting some regions, and then the next layer is going to do that again, and then you're creating kind of these geometric separations in the space of, okay.
That's exactly what happens.
Oh, that's very interesting.
If we had, for example, another point up there, like if it was needed another triangle, another line there to cut, would we have to only 2 height?
I think it's easier if I draw this. What do you mean by other points? I don't know if I got it, what you said. Okay, let's draw here. Okay, originally we have this, right?
Right.
What do you mean by another point?
If up there it was yellow, but in the middle all white. The yellow?
Another yellow here?
Instead of the white one.
Here,
yellow.
another yellow here?
Yeah, but in the middle white, so we couldn't draw a simple...
In the middle, another
white.
color? White.
So we couldn't just create a single line. It would have to have hidden.
Yeah, you have to find a good configuration to draw hyperplanes to be cut.
No, yes, in this example, only 2 hidden neurons would be enough, because in that example...
Maybe not, yeah.
Maybe not. No.
Let's think about, maybe not. Maybe you need more. Maybe you need more. Okay, and then you have more neurons in the output to make the combinations. Yeah, for example, that would be something like this, I don't know. And then you combine here and here, you already have a separation. See?
The question would be something like, can we calculate, how do we estimate the necessary number of hidden neurons? We don't
That's
know.
another difficult question, because this is a hyperparameter of your neural network. You don't know how many hidden neurons it is enough, okay, in complicated problems. You can try to do like a grid search. You start with a number of hidden neurons, then you perform experiments, for example, in a validation data set, and it increases, you make different tests, you increase the number of neurons in the hidden layer, doing many tests until you find a good configuration. It's more or less like a try and error procedure, okay? Is it okay?
Yeah, but usually with like biological systems and problems, how many neurons are usually used in these kinds of models? Like 10, 15, or hundreds?
For example, I have a student that he works with, I think the pronunciation in English is piRNA. It's a piRNA. piRNA. It's a small no-coding RNA, okay? We worked with neural networks that had, for example, 10 or 15 neurons in a hidden layer, and then another hidden layer with 10 hidden neurons, and it was enough to classify the RNAs, classify no-coding RNAs in being piRNAs or not, you know? Usually, if you have a lot of data, you can try to use a lot of hyperparameters if you have a lot of data, okay? Because if you have a very small amount of data and you use a neural network, a very big neural network with a lot of parameters, for sure you are going to overfit your data. Okay? Okay? Remember that trade-off bias variance. So if you have many wages, you are going to have a neural network with a very high variance depending on your data. So probably you are going to memorize your data. Okay, so you have to think about this trade-off, okay?
But what's a lot of data?
A lot of data, like thousands of instances, okay? Then you can make a bigger neural network. Okay. We have some toy problems where we have, for example, 60,000 instances. 60,000, that's a toy problem. Then we can try to make bigger neural networks. But if we have, for example, 200 instances, then that's not a big data set. We don't need a very big neural network. A small one will be enough.
I think I've seen people say that, like, to do these kinds of trainings of these large multi-layer networks, people usually parallelize the process, right?
Yeah,
But how do you parallelize this? Because everything is connected to everything, so it doesn't seem so easy, right?
But in one layer, you can compute the output in parallel.
Ah, okay.
Yeah, given one layer, you have all the outputs of the previous layer. You can compute all the nodes in parallel.
Yeah, okay, because it is actually one step is updating the entire layer, right? So
yeah.
Okay.
Mm-hmm.
Makes sense.
Is it okay? More questions? Let's go for some implementations. Okay. Ooh, what have I done? Whoa. Just a moment. Okay, let's go for the multi-layer perceptron. Ooh, there's a spoiler here. Okay, so I'm going to use, is the size okay? Yeah. I'm going to use two packages here. The first one's neural net, okay, and I'm going to try to use the package Keras. That's very good to work with neural networks, okay? Let's see if everything's correctly installed here. Yes, okay. I don't know if you have the Keras package installed. Yeah, you can try to install it with these two commands here, okay? But first, let's let's play a little bit with the neural network package, okay? Because it's a little bit annoying to install the keras, okay? So, okay. So what we are going to do first, we are going to play with some regression problems, okay? We are going to generate some numbers and see how we can, for example, compute here the square root of a number. A very simple problem, but just for you to see how to use the neural network, okay? So suppose here, I'm going to create a data set, okay, with 50 numbers. So I'm creating a data frame here, okay? Actually, I'm creating 200 numbers here, okay? Between 0 and 200. And then I'm computing the square root, okay? So this is going to be the one variable, a number, and the output is the square root. Okay. There we go. Now I'm concatenating the input and the output. Okay, just to make everything beautiful, I'm giving a names to the columns, and I'm printing here the data. So this is my data, okay? I have an input, and I have the square number of the number. Square root, sorry, of the number, okay? Nice. I'm going to train an artificial neural network here with one hidden layer having 10 neurons. And I'm going to have one output layer. Okay. So to do this, I just call the package neural net. I'm going to say that I'm going to train the output, okay, against the input. So the input is going to be used as predictor variables, and the outputs the target I want to predict. And I'm using 10 hidden layers. If I wanted more hidden layers, it was enough to pass a vector here. For example, 10, 5. Okay, 2 hidden layers. The first one with 10, the second one with 5 neurons. But I'm going to use just 1 here. Okay, and I can plot here my neural network. I'm training and plotting. Here. Okay, so these are the final wages. So we have wages connecting the input and the hidden layer, wages connecting the hidden layer and the output, and the bias, see? Okay. And here, see, the network trained it for 33,545 epochs and obtained this small error in the training set. Now we are going to test this neural network in a test data. So I'm going to generate here a test data, okay? I'm generating a data frame here with 10 numbers. So for example here, so test data is like, okay, some numbers, okay? Then I'm going to compute, okay, the square root of these numbers. Okay? So to make predictions, I'm going to use this function compute. I'm going to apply the network in the test data. Okay? And then I'm printing here the result of the network. Is the net result in the property here? This is a list, okay? And it has a position here that's net result, like a dictionary here. So I calculated the root of the numbers, okay? Now I'm going to show the results in a more clear format. What I'm going to do, I'm going to combine here. I'm going to make a matrix where I'm getting 2 columns together, okay? The test data, the square root of the test data, which are the true, okay, the desired output, and the results of the network. Okay, I'm just putting names here in the columns and printing the output. So C, pretty okay, right?
I tried to run it and I got the message warning. Algorithm did not converge in one repetitions of the step max.
You used exactly this.
Yes.
Yeah, maybe it didn't converge. You have to try to run again.
I tried.
Yeah, really? You have the same data?
Yes, I just run it to markdown here. Let me see. Yes.
It's strange. What's exactly the message?
Warning, algorithm did not converge in one of 4 repetitions of the step max.
You can try to increase the step max maybe. I think you have here a parameter. Oh, let me remember. Neural net. Here, step max. Maybe you can try to increase it. Then run again. You can try to do that. It's going to run for more interactions, more epochs. Okay? Because I'm not sure here also what's the stopping criterion that he's doing here, okay?
Oh, I was going to ask that. How is the stopping criteria? I think that in the documentation it says that the maximum number of steps, that I think it's 10 to the 5, but aren't we risking overfitting by performing a lot of steps?
Yeah, we are risking overfitting for sure. That's
Okay.
The ideal would be to have a data set, a validation data set, like to compute the error in the validation data set and stop
so
in a, I don't know, for example, define a stopping criteria that would be an acceptable error, for example. If I get an error below, I don't know, 0.001, then I'm going to stop.
Okay, so like plotting for like epochs, I don't know, the
Yeah,
errors.
that's not a good stopping criteria, like
Okay.
running for, I don't know, 1,000 epochs or something. That's not a good stopping criteria.
Because I guess that at one point it will start to like overfit the training data and maybe your accuracy on the test will be bad, right?
Yeah, exactly. Okay. Exactly that. So that's why in many occasions that the correct thing to do is to work with early stop. Okay, we define a stopping criteria, we change the learning rate with time, okay? As we go further in training, we start decreasing the learning rate, okay, to slowly the adjustment of the wages, okay? But you're right, the number of epochs is not a good criteria. We are just playing here. Let's see again. See? Did it run now? See? Okay. Now I'm going to try to do here some classifications using the IRIS data set. Let me see here if I'm working with before that, I'm going to try to work. Let's play a little bit more with this IRIS data set here. Okay. What I'm going to do here, I'm going to load the data, so this is the same, okay? Okay, I'm loading the data here. So what I'm doing here, I'm getting the IRIS data set, as I already know, okay? And I am combining, okay, in my model, what I am doing is that I am using here, I'm passing the categorical classes to numeric ones. Okay? Here. So I'm going to have a data set with the features and the classes as numeric vectors. Okay? And then I am changing again the number of the name of the column to speeches again. Okay? And I am scaling the data because now I want to perform classification. And here you see part of my data. Okay? Now here I'm separating. Just a minute, let me get some water. No. Okay. I'm going to separate my data here in training and test data sets, okay? Training and test data. So here again, this is we performed this before, right? You know how to do that. Okay, I'm just sampling numbers and indexing the data set as a training and test data, okay? Nice, and here's part of the data. Okay, now I'm going to do the following. Before doing that, okay, I'm going to still work with the neural net package. So what I'm going to do, I'm going to load here the data, where here, I'm going to do it again. Here, okay. So the net iris will be the neural net. And I am going to, let me remove this step max. Okay, I am to do, I don't know, let me see, a hidden neuron. So I have 4 features. Let's work with like 5 features, 5 hidden layers, maybe 3 here. I don't know, I'm guessing, okay? Let's work with 2 hidden layers here, just to see what happens. And I'm going to work with speeches against everything. Okay? And I'm going to work with the train data. I don't need to use as matrix aqui. Actually, I don't need to use as matrix. It can be a data frame. So I'm going to use here the train data. Train data, and I'm going to plot the net iris. Let's see what happens. Jesus Christ. Speeches. Ooh. This is my neural network. Okay? One important thing, okay? If you look at the documentation, let me see here. See? No, where is it? Where is it? Step max, no. Learning rate, start wages. There is a parameter here that's, if I'm not wrong, is linear neural net. linear output. You know, by default, linear output is true. Okay? So, the output of my neural network, okay, this is the output, okay? Here, probably, if I'm not wrong, the activation functions are the logistic, see? The activation function is the logistic, see? But I am not setting linear output to false. Why? I'm setting it to true. Because in my data set, I have the classes as numeric numbers. Remember, here are the speeches, 1, 2, and 3. So the output of my neural network, because I have only one neuron, has to be linear. Okay? It will be 1, 2, or 3. I'm going to learn a linear number. Okay? Further, we will try to do something different, but let's concentrate in this now. Okay, this is the neural network I just induced, okay? I don't know if it's a good neural network, but anyway, let's work with them. Now, okay, I'm going to test the data. So, just let me just here, training for Iris. Training for Iris. Now let's do some testing. Here. Compute, yes. Test the model. Now I'm going to test the model. Okay, so I don't need this because I already know my test data. Okay, I'm going to get my net iris and I'm going to get the test data. What's the test data? Test data, right? Okay, test data. But test data without the speeches. So I'm going to remove the last column, test data, right? I just removed the last column, minus number of columns of the test data. I just remove it. So I'm really applying the model here, and I am getting net result here. I'm going to see if I didn't do anything wrong. I'm going to see the output. Here is the output, okay? So let's check this output, okay? I have some numbers close to 1, I have some numbers close to 2, and I have some numbers close to 3. It seems to be working, but it missed some classes. Are you understanding? So what we are going to do here, so I just tested the model. Let's try to put the things, let's put the things here. Let's put the things in a more clear format. Nice. So what I'm going to do here is that I'm going to get the output, so net result. So this guy here is going to be our predictions, right? The true values are the test data species, okay? Okay. And actually what I'm going to do is that I'm going to construct, I don't know here, around, oh no, predicted class. I'm going to do a strange thing here, but it works. I'm going to round the predictions to be 1, 2, or 3, okay? Nice. Then I'm going to construct here a tab that's going to cbind, okay, the true values, the predicted class, and the predictions. Okay. And I'm just going to give some names here to this tab. That's going to be true, true, predicted, and I don't know, real predicted values, real predicted values, anyway. And I'm going to print the tab. See? Yeah, this should be rounded maybe to 1. Yeah, 0.4. This should be rounded to 1. Maybe I'm going to put, what's the function for? No, I don't want ceiling, I want the other. I forgot the word for the name of the function. Yeah, maybe ceiling puts it to, okay. So is this, that's this. Ceiling predictions, see? Ooh, ceiling, sorry. Yeah, but ceiling was not the right choice. Floor, yeah. Yeah. I'm get some zeros. These zeros should be, yeah, I don't like it. Round, let me see the round again. The round will give me 1s, 2s, and there is a 1, 0 here. That's a wrong prediction. That should be 1, okay? That means, you see, I had to construct a function that gives me a given class considering the output. Okay, that would be the correct. Let's try to play with our neural network. I don't know, 6 and 4 maybe. Seems we get better results. Okay, so see, it really depends on a trial and error. Okay, and now look at what I'm going to do. I'm going to construct here confusion matrix. You know what this is? So I'm going to construct here a confusion matrix. So what I'm going to do, I'm going to construct a table here. No, table is a function. Conf matrix. This conf matrix is just a table, okay, considering, yeah, I think it's going to predict to predicted class. I don't know if it's going to work. Yes. Conf matrix. So see, this is a confusion matrix, and I just missed one class in my test data set. Okay? With this, I can calculate an accuracy. How can I calculate the accuracy? The accuracy is just the sum, right, of the diagonal of the confusion matrix. Okay, divided by the sum of the confusion matrix. Okay, and this is my accuracy. So 97% of accuracy. Okay? Questions? Is it okay? Nice. So let's try to play a little bit, okay, with the Keras package. Let's see if we can do that, okay? So what I'm going to do here now, okay, I have to go back again here, and I get to do this again. I have to do this again, because I need a different command just because of Keras, okay? And I'm going to do an S matrix here, just because of Keras. So yeah, we have that. Ooh, no. No. Yeah, I have to load the data again because there's something wrong. Data iris, blah, blah, blah. Okay, head data iris. Now let's go back there. Oh, no. Data iris. Okay, these are my data again, okay? Good. Now I'm going to separate the features from the labels. Okay, I have the X-train, so see the training data without the label, and I have the Y-train, that is the label. Okay, and I put in -1 here because now I want my label to be 0, 1, 2 instead of 1, 2, 3. This is also necessary for Keras, okay? Nice. I'm doing the same for the test data set. Here. Okay, these are my classes of the training and test data. Okay, 0, 1, and 3. Okay. Now I'm going to define an artificial neural network here with 2 hidden layers having 4 and 3 neurons. To do this, I'm going to use this sequential API of the Keras. Are you familiar with Keras? So that's good, you're going to learn something new. So Keras is a library, I'm going to call it a library in Python that's built, if I'm not wrong, upon TensorFlow. That's a mathematical library, okay? And it makes easy for us to work with neural networks. So with this API, sequential API, you just go and add layers, okay? Easily, you can easily add layers, any kind of layer you want. So what I'm going to do here is that I'm constructing a model based on the sequential API. And see, I'm just adding a dense layer. What's a dense layer? It's a layer that we saw in our slides, totally connected, okay? So I'm adding a dense layer with 3 units, 3 hidden layers, and the activation function, I'm using the ReLU, that one I showed you, okay? In the input shape here, I'm saying that is the dimension, okay, number of columns, number of features of the training data. Nice. Then here, I'm just adding, see, another dense layer with 3 hidden layers. Okay, I put 4 and 3, so I'm going to put 4 here. With 3 hidden layers, and the activation is a softmax, that one I told you, because I want to model the probability of the classes. You know, the summation of the outputs of the layers will be equal to 1. Output of the hidden layer will be equal to 1. Okay, and here I'm doing the back propagation algorithm. Okay, I'm going to compile my model. I'm saying that the optimizer is the stochastic gradient descent with a learning rate equals 0.3. Okay, we saw that in the class. And then here I'm passing a loss function that's going to be used to compute the error of the neural network. This categorical cross entropy, okay? I think it's easier if I go to the internet and show you. Let's see, categorical cross entropy. entropy. I just want a formulation. Ooh. Now I just want a formulation. Yes, that's the categorical cross entropy. You see? Okay, I'm just doing the here. Here's a good see. This is a categorical cross entropy. I'm just computing the log, see, of the outputs. You know. Okay. So the output probability of belonging to the class, log of not belonging, 1 minus belonging, log 1 minus belonging, you know? Okay, so I'm going to compute this one. This is this function is that I'm going to compute. And why sparse? It's just sparse categorical cross entropy because of the format of the labels we are passing to the data. We are passing a vector like this. 1, 1, 1, 2, 2, 2. So it's a sparse format of passing the labels to our neural network. Internally, the neural network will convert this. Okay. Another format would be, for example, for each instance, I could have a vector of 3 positions. Okay. So, for example, if the first instance belonged to class 0, then I would have 1, 0, 0. That's the output for the first instance. If an instance belongs to class 2, then I would be, the label would be 1 here. Okay? Did you get it? Okay. So because I'm not using this format of modeling my labels, I have to use this sparse categorical cross entropy. Okay. Otherwise, I would use only cross entropy. Nice. And the metrics, I'm passing a metric here that's going to also to be used to calculate will be calculated in my training data. I'm going to calculate the accuracy. Okay. And here I'm presenting a summary of the model. So I'm compiling the model. And I think it's taking a little longer because of the first time I'm running. And it will show the model. Were you able to install Keras? Oh, okay. Come on, go. Oh. Come on, come on. It should have run. I don't know what's happening. Maybe that's because of the first time it is running. Okay.
I have to install Keras from Python. Is it correct? Or is there any way to
Yeah,
install
actually, Keras is from Python. I'm just here importing the Python code. Okay? Yeah. While it compiles here, I'm just show you the other code here. So what I'm doing here, I'm constructing a function that trains the model. Okay? So my model will be stored in this learning parameter here, okay, in this learning variable. So I'm going to get my model and I'm going to fit it. I'm going to use the training data as my training data, of course. Why train the labels as my labels? I'm going to train for 100 epochs. Bet size equals 1. That means that I'm going to pass the instances to the network one by one. Validation split means that I'm going to get the training data and use 20% of the data as validation. Remember I told you validation, okay? And verbose is just to show what's happening, okay? And then I'm going to return a list, that the learning model, okay? And the model itself, the learned model and the model itself. Okay, I don't know what's happening here. It should have trained it already. So I just want to run again. Jump into top level, what's happening? Whoa, no, it is here. Come on, it is here. TensorFlow Keras was not found. Oh, come on. I already did this. Yeah, it seems I'm not having here. Oh my God, what should I? Maybe I have to uninstall Keras. Come on, I thought I had already installed this. Come on. Yeah, while this is installing, I'm just going to show you the rest of the code, okay? Yes. See, I had trained this already, okay? That's why I'm telling you. See, here, when I trained the neural network, see, it was training here, and it was computing, you know, the accuracy and the loss function in the training data, and the accuracy and the loss function, okay, in the validation data set. And it trained it for 100 epochs, okay? See, epoch 40 of 100, and it trained it. So my stopping criteria was the number of epochs, so it trained it. And then I made some predictions. What I did, I get my model, okay, and use the function predict here, passing the test features, and then I obtain the predictions. So it's interesting to see that this model, this neural network, has 3 neurons in the output layer. Okay, 3 neurons. So with the softmax activation function in the output layer, what I have is that the summation of the outputs are 1, okay? Very close to 1, see. And I'm going to classify the data in the highest neuron. So, okay, 1, 0, 1, and 2. Okay? So now I got these predictions in the test data set, and what I did here, I combined it. I did the same thing I did before. I performed it around in the predictions and compared it to the true test values. So here are the comparisons. See. Okay. Look. So these are the predictions. And see, and this is the true class. Predictions, true class, predictions, true class. So the neural network is more or less okay. Okay. Then now here I put the predictions into a unique vector. Okay. So with this function here, okay, I apply the round predictions. Okay, in each row of that matrix predictions, and I returned the predictions in the format 1, 2, 3. Good. And then I calculated the accuracy. See, in the same way I did before. And I obtained an accuracy of 0.92. okay, because I missed here 3 instances. Okay. Now here I'm defining a neural network with a different architecture, and I am doing the same, see? And this is very interesting. I wanted to show this for you, okay? What I did here, I constructed a callback. A callback is a list of additional parameters, okay, that you can pass to your neural network for training. So for example, I'm doing here an early stopping. So I'm going to monitor the validation, the loss in the validation data set for 10 epochs. Oh, what have I done? Where are the callbacks? No. Yeah, here. I'm validating, I'm watching the loss function in the validation data set for 10 epochs, okay? If the validation doesn't improve, I mean, if the loss doesn't decrease after 10 epochs, then I stop training, okay? Here's another interesting thing. Look, I'm watching the learning rate on a plateau. What's a plateau in the learning function, in the error function? It's a surface, right? Okay, so I'm watching, I mean, if the validation loss doesn't decrease also for 10 epochs, I'm going to decrease the learning rate by a factor of 0.1. It's like multiply the learning rate by 0.1 and decrease the learning rate. Okay, it's interesting. And then I'm going to try, I trained the same neural network, but now calling this callback, you know. And when I did this, I see it was training, and see it stopped after 10 epochs from 2000 epochs, okay? So this tries to avoid the overfitting in the neural network. And then I can get the neural network trained and make some predictions. Okay, and now I did the same thing I did with the neural network without the callback. Okay, and see here are the predictions. Oh, what? No. Yeah, but these predictions, oh, this is, I'm doing this. Oh, this I performed this for the SNP data, sorry. I jumped it up. I just jumped a step here. I worked here with, remember that data set, SNP data set? I also run this neural network in our SNP data set. Okay? Remember the SNP data? We just loaded here the SNP data, okay? Separating training and test data. Look here, the SNP data, okay? But because I'm working with neural networks, remember, I had to convert, okay, the data for 0 and 1, remember that? Okay, I found the correlations, remember, I removed the high correlated features, remember that? Separated in training and test data, here, okay. Separated the features from training and test, okay. Defined here a neural network, see? Now it's going to work. Okay, created a callback here, trained the neural network, and then tested the neural network and calculated the mean square error. Okay, the root mean square error. It was 182 compared with our random forest. It was 174. So we got a little higher error, okay? We can try to improve the neural network, work with other hyperparameters, and so on. Let's see if I can run this neural network now. Yeah, I don't know what's happening to, I don't know. I think it did install. I think it did install the library. Yeah, I don't know. For some reason, it didn't install the library. But you got it. Maybe now it's going to work. Oh, come on. Did you understand what are the stopping criteria, the callback functions, okay, how to use the neural networks in your data? That was the main purpose, okay? Yeah. Was it okay? Do you have questions? No questions? Did you understand how to use the caras, how to add layers? Okay. You can try many different things, like for example, adding, if you have a lot of data, you can try to add dropout. Dropout is another thing that you use to avoid overfitting and improve generalization. Dropout is just used to like kill some of the neurons, okay? And then with this, you try to improve the generalization ability of the neural network because you try to force the neurons to learn without the presence of other neurons, okay? Questions?
When adding layers, they're just sequential. And the sequence that I put in the code is the same as they're going to appear in the model, right?
Mm-hmm.
So it's the same, okay.
Yeah, there is another API that's a functional API, okay? It's better than this one because you can access the layers in the middle of the network. Okay, so for example, you can construct a neural network and then you can access the outputs of some hidden layers. And actually, when you do this, you are extracting features of your data. You know, you are extracting features, and these extracted features can be used as input to other classifiers. Okay, so remember that idea that the layers are feature extractors. So you can, for example, reduce the dimensionality of your data by extracting features of your original data. Okay. Yeah, you know, I don't know what happened. Installation complete. Resuming our section. And then I don't know if I have to like run this again. And now try to run this again. Yeah, I really don't know what's happening here this time. Maybe it's a problem here with my installation, I don't know. Are we in time? Okay, so hope you have enjoyed the time we spent together. I hope the things you learned here, I hope you learned new things and that you can use that in anything you're going to do, okay? And if you have questions you want to have, don't know, for anything you can just mail me. I'm happy to talk to you, okay?